Hello, geometry students. It is so nice to see you again. I am happy to be able to make another video for you on our geometry lessons. Chapter 8 is kind of a short chapter. We only have a few sections in it. We've done sections 8.1 and 8.2. In our last lesson, we learned how to prove two triangles are similar using something called AA, which we know stands for angle. Today, we're going to learn two more shortcuts, SSS and SAS. Now these read the same as our congruent statements that we learned before did, so side, 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 and side, angle, side, but they have a slightly different application. So we'll do the theorems first, and then we'll do several examples to make sure that you feel comfortable with it. So the side, 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 and I'm going to be lazy here and write similarity by that. Similarity theorem tells us if we have three pairs of corresponding sides that are proportional, then the triangles are similar. So let me show you what I mean by that using a specific example. Let's say that I have one triangle with lengths 6, 8, and 12 for its sides, and another triangle with lengths 3, 4, and 6. What I need in order to be able to prove similarity using side, side, side is I need three pairs of corresponding sides that are proportional. So if we look at this problem here, we can see that whenever we divide a side on the left by a side on the right, we get the same number. Let's look at that. So we can say since 6 over 3 is equal to 8 over 4 is equal to 12 over 6 is equal to, 6 over 3 is equal to 2 over 1. Since they are proportional and all of the sides have the same ratio, we can say the triangles are similar. Okay, now if we want to do the side angle side similarity theorem, it is kind of the same idea, but there's a little bit of a difference here in that we only need two sides and an angle. Notice, however, that the angle has to be what we call the included angle. It has to be between the two sides. So if we wanted to check whether or not these two triangles were similar using side, angle, side, we would compare the two sides and we would need the angle in between to be congruent. So we've got the angle in between congruent, then we just need to see the ratios when we compare the sides. So is 9 over 3 the same as 12 over 4? Yes. Both of those ratios are equivalent to the number 3. So those two triangles will be similar by side, angle, side. All right, so let's do just a few examples of these theorems, and then you guys will be good to go for the notes for today. So let's go ahead and look at example number 1. The directions say, use the given information to determine whether each pair of triangles is similar. If so, write a similarity statement and justify your answer. All right, so let's draw our two triangles. We have triangle LMN, and the information given is sides of 8 and 12 with an included angle. And then we have triangle STU with side lengths of 6 and 9 and also an included angle. So we need to check to see whether or not the sides are proportional. We're going to compare 12 over 9 to 8 over 6. And the question is, are those the same? Well, an easy way to do this is to reduce each. 12 over 9 can be divided top and bottom by 3, so that becomes 4 over 3. And 8 and 6 can both be divided by 2, and that also becomes 4 over 3. Another method, if you prefer, is to cross multiply and see that you get the same answer. But we would say yes by side, angle, side. Our similarity statement could be that triangle LMN is similar to triangle TSU. Again, we just need to make sure that the angles are listed in the appropriate order. So that, for example, since L is first here and T is first there, L and T are the ones that are congruent. All right, let's do example number 2. So example number 2, again, I've got 2 triangles, and the question is, are they similar? Yes or no? If so, why? And then, what is your similarity statement? So let's go ahead and draw triangle ABC, and then triangle DEF. So these are both isosceles triangles. So we have less actual work to do, because when we take 6 divided by 9 there, that would be the same that we would get for this pair. So all we really need to compare is C is 6 over 9, the same thing as 8 over 12. So we can say since 6 over 9 is equal to 8 over 12 is equal to 2/3, they're both equal to 2/3, the triangles are similar by side, side, side. And again, you can see the 2/3 there if you want by dividing top and bottom of this one by 3 and top and bottom of this one by 4. Now your similarity statement could be, for example, triangle ABC is similar to triangle DEF. You know, depending on how the triangles are labeled, you may or may not go alphabetically. So don't always assume that it will be alphabetical. It often is the case, but it doesn't have to be. Okay, let's go ahead and take a look at another example. This will be example number 3. And we want to find the value of x that makes the triangles similar. So here we are not being told that the triangles are similar. We're being asked to say, what would you need to make x be so that they would be similar? So the trick here is to notice which sides correspond to what. So we can see on this triangle that the shortest side is 3. That is going to correspond to the shortest side on the other one. And of course, I didn't draw this triangle perfectly. I probably should try to draw it a little bit more to scale. There we go. And then we can see that there's also a medium-sized leg on this triangle that would need to correspond to the medium-sized one over here. And then finally, there is the longest side on this triangle would need to correspond to the longest side on this one. Now I want to see what my scale factor would need to be in order for these triangles to be similar. Scale factor means side divided by side, and it has to be a corresponding side. So if I want to compare 4 on this triangle to a side on the other triangle, I would have to be comparing it to the 8. So I can see that 4 divided by 8 is 1/2. If these triangles were similar, it would need to be that every side on the left divided by a side on the right would have to equal 1/2. So let's do that with this pair right here. I need 3 over x plus 3 to equal 1/2. Now to solve this, I can cross multiply. So 1 times x plus 3 is just x plus 3. And then 3 times 2 is 6. And then I subtract 3, and I get that x equals 3. Let's try putting the numbers in. If I put 3 in here, 3 plus 3 would be 6. Is 3 divided by 6 1/2? Yes. Now, let's try looking at the other dimension. So if we write, oh, and you know what? I did another typo. This was supposed to be x plus 2. That doesn't really help. So let's put in 3 here. If we do 3 plus 2, we would get 5. And 5 divided by 10 would also be 1/2. So these triangles would be similar if x was 3. Okay, let's go ahead and do example number 4. We have 2 more examples, 4 and 5. All right, so for example number 4, it says verify that triangle ABC is similar to triangle DEF. So I want to verify that ABC is similar to DEF and find the scale factor. So for triangle, what I'm going to do to answer this, the problem does not give me a picture, but I'm going to draw one. And since they said that ABC was similar to DEF, I'm going to make sure that I label the angles in the same order on both. Now, it says in the directions that AB is 20 and that BC is 28 and that AC is 24. And let's see, AB is 20, BC is 28, AC is 24. Oh, and then in triangle DEF, DE is 35, EF is 49, and DF is 42. Now, to verify that these 2 triangles are similar, I need to show that the scale factor that each side on the left divided by its corresponding side on the right is going to equal the same number, which is the scale factor for the 2. So let's say we want to show that 20 divided by 35 is going to be the same thing as 28 divided by 49, and that is going to be the same thing as 24 divided by 42. Let's see if this works. If we look at the first fraction, 5 goes into both of those numbers. So dividing by 5 would give me 4 over 7. In this fraction, 7 goes into both, and that reduces to 4 over 7. And in this fraction, 6 goes into both, and that also reduces to 4 over 7. So since all pairs of corresponding sides are the same ratio, we can say that they are similar by side, 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 and we can also say that the scale factor is equal to 4 over 7, keeping in mind that scale factor simply means side divided by side. Okay, we're going to do one more problem, and then we will be done with our notes on 8.3. So this is going to be problem number 5. And there's going to be several parts to it. I think I'm going to erase this, so freeze the video if you need to take a picture of that or do anything more. And then that way we'll just have a little bit more room to work with. So I'm going to draw a diagram for number 5. And then label it with the appropriate letters. So we have W, X, Y, Z, and V. So it's kind of a weird looking shape here. This angle is 24.5. This one is labeled as 65.5. And remember, anytime you see a shape in geometry, you cannot assume that it's drawn to scale. It may be, but there's also a good possibility that it's not. 24, 32 degrees. Okay, I'm trying to see if we have anything missing. I don't think so. I think we're good. Okay, so it says copy and complete the statement. So we have triangle VWZ is similar to triangle what? Let's use some colors to highlight this. If we look at VWZ, we can go from V to W to Z and highlight that one. We need to see what triangle that would be similar to. Okay, well, just looking at the picture, if these were going to be similar, then it needs to be similar to XYZ because these 2 angles will be congruent here. And we can check to make sure that the other angles are congruent by adding these 2 together. If I take 24.5 and add it to 65.5, that's 90 degrees. So that means that this angle here would be 90. And then this angle here would also be 90. And then from there, I can see that these two angles also would have to be 90. So all four of those angles would end up being 90. Okay, and then let's see. In order to find let's do the next step. The next step says, what is the angle VZY? So VZY is going to be this angle here, which we've already said is 90 degrees, so that's good on that one. So the measure of that is 90 degrees. On the next one, oh, and you know what, here on these two triangles, if we wanted to say Y, let's put the rest of the similarity statement. Let's write down X, Y, Z. Let's just say Y. I know it didn't ask us to do that, but the reasoning there would be side angle side. If you look at this triangle, we have an 18 and a 24 here, and a 12 and a 9 there. Now it's kind of flipped a little bit, but you can see that 18 over 9 is the same thing as 24 divided by 12 is the same thing as 1. The scale factor between these is 2 to 1 because we do have a pair of corresponding sides. So this would be by side angle side. Originally I was looking for a second angle there, but I don't think we can necessarily find these angles, but once we know they're similar, we can. But in order to see they're similar, all we would have needed is that right angle and this right angle here, and then the sides on either side of them. So we've got the two triangles similar. We figured out the measure of that missing angle. Let's see part C. That was A, this is B. Part C says to find the measure of angle VWY. So let's look at it. VWY. That would be this angle right here. And then the next one after that, let's write these all out. The next one after that is going to be to find the measure of angle WXY. So let's see here. WXY. That would be this entire angle there. And then the last part E, is asking us to find the length of XY. Okay, so now that we can kind of see that these two triangles here are similar, we know they're similar by side angle side. We know that all three of their angles have to be congruent. These are already 90 here. This angle 32 is going to correspond to this angle up here, which is also going to be 32. And then what that means is if I take 90 plus 32, I'm going to get 122, which means that if I subtract that from 180, this will be 58 here, and that will be 58 there. So I think the first number is what we're going to put here, and then WXY would be 65.5 plus 32, so 65.5 plus 32 would be 97.5. And then if we look at side XY, this is kind of interesting. This side here is 720, and this is the side that we're trying to find right here. We know that those are corresponding sides on similar triangles. We also know the scale factor is 2 to 1. So when I take the square root of 720 divided by my missing side, let's call that, I don't know, just little x, I guess. 720 divided by x would have to be 2 over 1. Now, let's do a factor tree for 720. I think I'll do it over here because there's a little bit more room. If I do a factor tree for 720, 2 goes in 360 times, 2 goes in 180 times, 2 goes in 90 times, 2 goes in 45 times, 3 goes in 15 times, and 3 goes in 5 times. So the square root of 720 is the same thing as the square root of, let's count how many 2's we have here. 1, 2, 3, 4, it looks like 4 2's. And it looks like a pair of 3's as well, and a 5. So remember, anytime we have a pair, we can pull that out. I'm going to pull out that pair, and this pair. When I do, I have 2 times 2 times 3 times radical 5. 2 times 2 is 4, times 3 is 12. That is going to be 12 radical 5. So this 720 square root simplified is 12 radical 5. So over here, I'm going to write this as 12 radical 5 over what would be 2 over 1. Now I can cross multiply. So I know that 2 times x is 12 radical 5. And then when I divide both sides by 2, I can see that x would have to be 6 radical 5. That was pretty intense. But what that means is that this side right here needs to be 6 radical 5. Now, if you hung with me through that example, I am super proud of you guys. I know that was a pretty long one, but I think if you can do that one, you can probably do any homework in this section. Thanks for doing all that work, and I'll look forward to seeing you soon. Bye, guys.